So we finally come to one of the most important concepts in AP statistics and in all of statistics, and that's density curves and, more importantly, the normal distribution. So let's start talking about what are these density curves in the first place. The first description we use for a density curve is that it is always on or above the horizontal axis. We actually have two examples of density curves down here, and you can see that all of our data is represented above these horizontal axes. However, if we think about it, all of our data so far, histograms especially, have always been above a horizontal axis. So this is just a representation of that same data. The next thing that describes a density curve is that it has an area of 1 or 100% underneath the curve. So all of our area under here is 100% of our data, or represents it. Now, one thing to keep in mind is that since this is an approximation, if I actually did like a histogram of my data, some of these bars might fall below and above, so it's just an approximation. So it's kind of an average representation. That's a bad histogram. I'm not going to keep that there. But it just kind of gives you an idea of it's just a stylization of the overall pattern of our distribution. All right, that being said, I'm going to put this side note over here because no distribution actually has these shapes. What these are curves that are approximations that just make it easier to find proportions of data. And we're going to talk a little bit more about that. So like I just drew that histogram, it doesn't exactly fit under this curve, but what it does is it kind of mimics the average. So some of our data might actually be above this curve, and some actually might be below it, but it's kind of an average. If we took the overall average of that shape and made it a curve, this would be a representation of that. So it's important to remember that a density curve is just describing the overall pattern of a distribution. All right, first, describing our density curves is since the density curves are idealized patterns, outliers are not going to be distinguishable. So for example, this curve here might have some outliers out here, but since it's just a blended, just a description of our curve, we really can't tell if there's any outliers or not. So you do not need to mention outliers. You still do need to describe the center, so you need to approximate the center. Just like our other distributions, if you have a skewed data set, your mean will be pulled to the right or the left, depending on the skew. It is an estimate. You can still describe these using our three: shape, center, and spread. So for example, the shape here is definitely symmetric and unimodal. This one is skewed right. Also unimodal. You could see a density curve with a little blip and be bimodal or multimodal. Also your center, mean and median. Median would be better in skewed data. However, let's talk about what's going on with the density curves here with median and mean. So for the median, when we're looking at a density curve, 50% of our data is going to fall on each side of the median, just like we think about when we're talking about a median and our data distribution, but exactly 50% of the area. So if we actually calculated the area of this curve, so if this were considered an area, it would be 50% of the physical area from here would be below the median and 50% would be above the median. Now the mean has a different property. If the data actually had a weight, and if you think about it, the data on this side is going to weigh less because they're smaller values overall than the data on this side. This would be heavier. So if this were actually physically weighted, the weight over here would be larger than the weight over here, because remember, the data itself, we would give the data itself some weight. So this would be, if we actually had to balance this on a fulcrum, those of you who know your physics, this were a fulcrum, then 50% of our weight would be on this side. Or sorry, our balancing point, it wouldn't be 50, well, yeah, I guess it would, 50% of our weight would be on this side and the other would be on that side. So just think about that a little bit differently, that mean is where this would balance perfectly. All right, getting back to our description though, we're going to use some new data symbols. So because this is an estimate of our data, we're going to use two new symbols. And I want you to see me draw these. The first one is mu. So the way you pronounce that, it's a Greek letter, mu. And I hope you kind of watched how I drew that. So from the bottom up. So it is kind of a really fancy M. And that is now our new symbol for mean when we're using these density curves. The other one is going to be sigma. So let me show you how I drew that again. Just start at the center and scoop it up there. So this is sigma. All right, and that is going to be our standard deviation. So this brings us to the most famous of all density curves, called the normal density curve. Now notice that normal is always capitalized. I'm not sure why. I actually tried to find it in your textbook. I couldn't find anything if it's named after somebody. I don't know. I'm sure if I Google searched it, I could find out. So let me know if you do. So all normal distributions are symmetric, unimodal, and bell-shaped. So we can see an example right here. All right, it's shaped like a bell. It's unimodal, one peak only, and it's extremely symmetric. So since all normal distributions have the same shape, we don't need to describe that, but we do need to describe its mean, which we're going to use mu from now on, and its standard deviation. There is an abbreviation for that, so we don't even have to write out the words. We put a capital N, and then next to it we put the numbers for the mu, for the mean, and the sigma standard deviation. So any statistician would know when I wrote those symbols, I'm talking about a normal curve with a mean and a standard deviation that is given. This gives us now the 68, 95, 99.7 rule. This is also known as the empirical rule. This simply states that 68% of all of our data in a normal distribution, this is only true of normal distributions, falls within one standard deviation of the mean. So 68% of our data. Now, those of you who took calculus, what's kind of neat about these normal curves is one standard deviation in the curve happens when our curve actually changes direction, where it goes from concave down to concave up. And in calculus, we call that a point of inflection. So a POI, a point of inflection. Now, if you didn't take calculus, this isn't really important to know, but it's interesting because these values actually do come from a little bit of calculus and the shape of this curve. There is some tie-in there. We don't need calculus for AP statistics, but it's just kind of interesting that there are some overlap. So continuing on, we can see that two standard deviations, that is 95% of my data. So the overwhelming majority of my data falls between two standard deviations of each side of the mean. And then finally, three standard deviations is 99.7. I'm just going to say this right now. This is something you need to memorize. So memorize these three numbers, 68, 95, 99.7. One thing you're going to be asked to do in AP statistics is you're going to have to be able to actually sketch your own curve from time to time. And this is not easy to do if you're not terribly artistic. So I'm going to give you some tips here. We, of course, are going to start with just a number line. And even that, as you can see, can sometimes be challenging. But this is not about perfection, but it is about actually being able to mark it well. So I'm going to go ahead and do a normal curve here. Now notice this, we want to do an approximately normal. We've got our mean, which is mu, and right here we've got our standard deviation, our sigma. And what I would suggest is kind of decide where you're going to put your mean. So my mean's going to be here in the middle, and I'm actually going to put a value there in just a moment. And then just above it, put a point. And from that point, you're going to make your curve down to your line. And then try to mirror that the other way. I see a lot of students try to do it this way, and as you can see, it's really hard to get that bell shape if you just start one side. So try to start at the top and just mirror each side. It doesn't need to be perfect. Then what we're going to do is you always start with your mean here, and we're going to write that in the middle. And then we're actually going to try to find that point of inflection, which would give me my first standard deviation. So it's right about there and there. And then from there, I can just do 3 standard deviations about the same distance. There we go. All right, and then you need to add or subtract your standard deviation from your mean. So let's start by adding on the right side. So 69 plus 2.5 would give me 71.5, and then 71.5 plus 2.5 is now 74, and then plus 2.5 is 76.5. And I don't know why I crossed that one and not those, but I did. Then we're going to subtract, so 69 minus 2.5 would be 66.5, and subtract again, and that gives me 64, and then subtract again, and that gives me 61.5. This is an actual skill you need to be able to demonstrate for the AP exam. All right, we're really going to break down the curve now into all of its parts using the empirical rule. So we've got the 68, 95, 99.7 rule, and we're going to just break down this curve as much as we can into its parts. So we're going to start in the middle at our mean, but we're just going to say for anything, we're just going to start there at 0. Then over here, this would be 1 standard deviation above our mean, and then we've got 2 standard deviations and 3 standard deviations over here. All right, and then we call these negative over here, so a negative standard deviation, so that just means below the mean, and we talked about that earlier. That's exactly what a negative standard deviation is. It's a value below the mean. Okay, and I'm going to mark that off there and there. Pretty straight. Then let's break this down into all of its percents. So if you remember, from here to here, from -1 to 1 would be 68% of my data. So if I wanted to know just from here to here for one of these parts, I would cut that in half, and this would be 34% of my data on each side here. Okay. Now from here to here, from 2 standard deviations on either side, is a total of 95%. So what I actually did was I took 95% minus the 68, and I figured out how much area was in each one of these parts. And what that ends up being is 13.5%. So that's the proportion of my data. You could also write this as decimals. To find the next area in here, all right, so these areas, what I'm going to do is the same kind of idea. I'm going to take 99.7, subtract 95 from it. That would be this little bit of area on both sides, but then I need to divide by 2 to get each side. And that gives me 2.35% in these little tiny bits here. Now, don't forget, we still have a little bit of area that falls just outside this 3 standard deviations, because that's what accounts for this 0.3. So this 0.3 now is going to be divided in half, and that's going to give me 0.15%. So there's hardly any data over on these tails, these very tips that are so extreme they fall outside 3 standard deviations in a normal distribution. This is not true of all distributions. We can now use this to answer this first question. So from -1 standard deviation to 2 standard deviations. So from here to here. Well, we know in this middle, from -1 to 1, that's 68%. So 68 plus, we have this little bit extra, so plus 13.5. And that, of course, gives us 81.5. So 81.5% falls within these 3 standard deviations in the center. So make sure they're in the center, and this could go the other direction as well. All values below 0, and they're talking about this 0 here, that of course everything below 0 would be 50% of our data. That would be the area there. The next one, so from -3 standard deviations to 1. Now be careful, don't just go, oh, well, that's 50% plus the 34%. It is not, because you do not include this little 0.15. So there's lots of different ways you could handle this. So I'm just going to add together these two sections. So 2.35, 13.5, and then I know from here to here is 68. So I'm just going to put that as 68. And that'll give me 83.85%. And my final one is when I'm looking at my values less than 2 standard deviations, it would be easier to just subtract this area. So that would be 100 minus, it's going to be 2.5. So that would be 97.5%. And finally, how can you use a normal probability plot? I'm actually going to show you some normal probability plots in class, but I would highly suggest looking through these pages in your textbook so you can see what they look like. But basically, they're just used to tell whether your data actually is normal or has a normal approximation. If the points of a normal probability plot lie close to a straight line, then the data are approximately normally distributed. So normal probability plot is a very complex, you never have to make one by hand, you'll just have to interpret them. What they do is they turn every value in your data into a percentile, and then it compares those percentiles to the expected normal values, and the closer those normal values fall to a straight line, then the more normal the data is.